good. So we'll now continue with another great talk. We are very happy to be hosting Dr. Danda Paudel from the same institution. I'll just very briefly go over super compressed bio. Dr. Paudel graduated from the CNRS in France in 2016. Then he joined ETH Zurich, I guess first as postdoc, then later as senior researcher and late lecturer. I think he's still with ETH Zurich, but he's also with INSAIT. I don't know if that's the right pronunciation.
Good.
Since 2023. Thank you very much for being here. I leave the floor.
Yep, thank you very much. I'm very happy to be here and thanks for hosting. And it's amazing campus around, and hope I will also have some time to walk around. And we've been talking about coming to here for some time. Thankfully now it worked out, and we are really enjoying here. All right, today's my talk will be about video world models with log context. Please feel free to interrupt me anytime. I would like to keep it more interactive. A lot of things I'm going to present is going to be quite preliminary, I would say. Hope that has a good motivation to us robotics eventually. Actually, I was thinking of presenting on vision, language, and action models. Possibly would have better alignment here, but then that I counted on Umut, that he was at INSAIT this summer, and he also worked on vision, language, action models things, and I hope he already told you about this. Therefore, I give the job to Umut, and I will talk about the world models instead. Okay, it is indeed a lot of motivation from robotics. I hope I will be able to convince you. Before I begin though, just quick overview for somebody who doesn't know about INSAIT. We are a very new institute, as Nicola said. Close collaboration with ETH and EPFL for 3 years, and we have got 10 years of partnership and the funding from the government of Bulgaria, and partnership with ETH and EPFL together with other labs around the world. Soon after the conception of the institute, we joined the ELIS network. Most of you may know this is the networks of the European Institute. Then we are one of the first ones actually in the Eastern Europe. And then we have different verticals of research, and one is on the trustworthy AI, other is quantum computing, and third one is computer vision, robotics, computer vision, and fourth one is generative AI. Me, Nicola, Professor Luc Bangul, and few others do work on computer vision and generative AI more altogether. And this we divide into 4 different categories. One is the vision language, one is about the multimodal robotics, edge and space AI, and generative models. All these we are thinking in the foundation model settings. As you may already know, that foundation models means that you build something that you can later on use it in different tasks across the board with much less of efforts. Okay, in relation to today's talk though, I want to motivate showing this particular video. This is not the video we generated, this is the video from DeepMind, and some of you may have already seen. This is like Sora, but not quite, because here you can see the buttons that you can actually decide what you want to do in this video. In this case, the person wants to now, they open the door of the car and the door opens, right? So this way that you are trying to move the camera directions, bringing close, bringing it far, going it around, actually interacting with the scene. And this is what I refer in the context of today's talk at the video world models, where you are not generating videos, but you are also generating interactive videos. And maybe it's quite obvious to you now already that if one can have very good interactive video like this, then possibly can be used for robotics, also for robotic simulation, right? I'll try to come back and forth from there on to here, but this work is actually done by guys at the DeepMind who don't share their code or the model, only show the results, right? So So outline of the today's talk today will be about in 3 different parts. One is really about slightly more a brief introduction of the video world models, and then 2 parts for on the generative interactive environments, and then we have done 2 set of works. I'll rather quickly jump into the next slide. All right. So what is this very philosophical motivation of video generative models is that when I sleep, I still see things. It means I don't have to open my eyes to see things, but in different ways, right? So somehow my mind has its eyes, right? And then maybe that's how we operate most of the times, and once in a while we see, and then we have to now somehow be in sync between what my mind sees and what my eye sees, right? And then the world model here is more about what does my mind see, right? There is the quotation which is not perfectly in line to the current literature, but I'll read it out. The image of the world around us, which we carry in our head, is just a model. Nobody in his head imagines all the world, government or country. He has only selected concepts and relationships between them and uses those those to represent the real systems. So we have some mental model of the world, and we basically operate using that. That mental model could vary a lot, right? So could vary of something very abstract like this apple, this word apple, right? Could be some sketch of apple and slightly more details, and then very, very fine-grained details of the apple. And there is a debate, both scientific and philosophical debate, is that what level of things that you actually represent in your mind. And for us, at least for me personally, that we can actually go all the way up to here. Otherwise, a very genius artist would not be able to paint very realistic things, right, without looking at it, unless they could really create in their mind. So we do indeed have capabilities of representing across the board all the way to the visual aspects. So that's why the previous video I showed you is indeed a mental model of what we could, or what our system could possibly do. So now to give it a slightly more of a technical touch, then let's categorize the visual worlds. And one visual world is when we open our eyes, what we see is the real world. That's the real world visual world. The good thing about it is it's very realistic, but the world itself may not be slow, but the way that we interact with the world is slow. It's expensive to interact, and so on and so forth, right? The world model, capturing, dealing with it, learning from it is slow and expensive. So another one could be the virtual environments. Okay, I don't want to go through jargons, but the point is that there are 2 kinds the way we categorize, not the right ones. One way is the virtual environments. Maybe I go by examples like blenders, right? Blender is not a simulator, but it can still render things visually meaningful. So that's what we call virtual environments like blenders. And then what we call other one is the simulators, like the gazebo like simulators, or more realistic simulators that in the robotics or in the autonomous driving, something like WMAX, right? So these simulators are in a way our expression more explicitly done of our mental representation of the real world, right? So basically we are trying to digitally capture these things by building the simulators, and then that may always be incomplete. So what do if we stop making our own simulators, rather learn to build simulators, right, from the data? Yeah, so that's where I come down to. It's all about data-driven simulators is what you want to build, and arguably these are those kind of simulators. Again, as I said from the beginning, these are the preliminary simulators that hopefully will take us far beyond than what simulators that we can have in the computers these days. Okay, so for most of you, I'm sure you know about the video generations, and world models do, especially the video world models, do overlap with them. I don't think they have this kind of distinction the way I put it down there, but some of this current trend of people dealing with them gives them the distinctive features, and that's how I categorize here by saying that this is mostly for the content generations. Maybe you want to build some kind of a Hollywood movie, This is more towards the visual realism, and you want to do so by conditioning over image or text, and then you more care about the visual features, right? And on the other hand, world models that we care within the context of data-driven simulators is about this dynamic simulations, behavioralism, dense action interactions, and world states. That's the case that we'd be caring about in this direction. So as I said, there will be two parts. Let's begin more on technical sides on generative interactive environments. And again, I go back to the previous video I showed you, now this time through the paper. This is the paper Genie. That's the video I showed you before from DeepMind. What it does, how it does, right? So this paper, essentially what it does is it takes the video. This is the video of people playing video games, like you go in YouTube and find a bunch of video games that people play, and then try to essentially branch it out onto two parts. One is part of the visual part, one part is the action parts, right? And then you recompose and make sure that you can actually get it back. It's something like auto encoders, right? You are making auto encoders, taking these people playing video games and embedding into the visual space and action space, and you hope you can somehow decompose the actions the way that you want, right? So what is interesting about this work, and what I want to highlight, is how cleverly do they this latent action modeling, that how do they decompose in latent space, right? So they assume that you cannot record the actions people when they are playing. You know that there are a discrete set of choices people have to make, but somehow you cannot record them. Let's assume so, right? Then what they do is, I will make this action space very limited in choice, like discrete, very few limitations, very few options you can have. Make these choices, right? And then I take the video frames from 1 to t here. This is one block, and this is the next video frame, right? So what I'm giving to this latent action model encoder is the whole video, including the current frame, right? And asking it to predict whatever action that has happened between t and t plus 1. So it gets to see what happens between these two frames, right? But once the action is obtained here, this decoder now needs to predict me the next frame without seeing the current frame, this t plus 1 frame, without seeing this, only from this particular box. So the assumption here is that the action is the only thing that makes a difference, right? So then it can actually predict this kind of action in very, very limited space and make use of that and whole history from before and combine them together and get the x t plus 1. And then now you can compute the loss, and therefore you can now make sense of these actions as soon as you limit them into this latent space of the actions. All right, so these are the results that they obtained in the Genie, I think 1 or Genie 2 actually. It is trained on many game engines. The what you call this multi-environment model. Genie is a multi-environment model that demonstrates high visual quality and controllability. That's basically what I talked before has been implemented. And then they take this model, since it works, then they scale it up. That's the current trend of modern AI, right? So if it works, then put more data to it. And how to play this? No, this is not this one. Yeah, here. So action here is actually somebody has this paintbrush in their hand, and then you are actually asking them to put it up and down. This one, and then you are asking it to go left and right, depending upon where you are. And this is all generated, and now you can actually make somebody paint on the wall, go around, come back, and continue painting. So there may be more than what I explained you before. That was the part of the Genie 2 in Genie 3, but that is all closed source. So this is all the information that we have, but it's largely what is believed is that large scale training of Gini 2 is what Gini 3, right. All right. So it's a closed source, it's just especially that Gini 2 we know about 11 billion model. It's a closed source trained on hundreds of TPUs, and it uses a curated data set, and there are 25 contributors in Gini 2. And since it's closed source, then it looks like we don't really have much of the hope, right. So what we did in the beginning, well, in the last year, is that let's just implement Gini by ourselves, right. Whatever it takes, we implement, make it open source, and so that everybody can develop something like Gini 2. So what we realized though is that maybe we don't have to begin by making it super complicated. Let's assume that you can record the actions of the people every single time just to create a benchmark. And actually we did experiment in different settings to make it cost effective, to make it open source. This is largely to begin with. The first part was the reproduction of Gini. For that we gather 1,000 environments. That's basically 1,000 environments, 1,000 different games, right. So just collected data from there. And what we realize is that okay, we don't know who was playing those video games in Gini settings, but for us either we need to find somebody who plays video games for us, or we decided rather let's not do that. We make a random model, just basically completely random agents that randomly plays games, right, inside, and that's how we began. And later on to decide maybe we can do something better than just random agents playing the game in these environments. That was the work that we presented at CVPR 25. It's called exploration driven generative interactive environments. So a little bit more about the data, that we were aiming for exactly 1,000 environments, and something goes wrong at times. Therefore we ended up with 974 environments, 974 game engines, you can say, well, engines. And then there were different kind of annotation necessary, what kind of game it is. Maybe you want to make it aware that some games have shooting, some games it can jump, some games you are seeing from the third person view, some games you are seeing from the top. All these kind of annotations we did so that people can make use of them. We don't necessarily use these all the labels all the time, but this is what we made it available. This is how it looks like. So these are all different environments. Every tiny block means one game. And we start by having this random agent. Random agent can generate random videos, right. So then we just train on those random videos. We don't really have any meaningful videos, so as to say. So this is the ground truth of this random agent. Therefore you see this doesn't look like playing a game but doing some actions, right, on the top, the ground truth itself. And this is the prediction which matches to the ground truth, but it's not really interesting, but it shows that you can learn things. You can see you can learn things like, for example, if you have this input, it can do something like left. These are the left. It's okay, I think you cannot really see much. This is going down, this one is jumping, right. You can see those things you can learn. Okay, this is the first part. You have the data set, you have an agent that does random things in the games, it plays randomly the games, dies all the time if it's something the game that dies, right. And then you have some kind of models which does okay job. And I think it's not really much anything new or groundbreaking to just decide that let's just not have this agent to be random. Let's just use some RL agents for it to train these agents, right. So then also it didn't make so much of sense for us because training one RL agent per environment and doing that right turns out to be very, very hard. We actually tried. Turns out very, very hard. So what we decided rather is that we make this random agent play the game and then do some sort of metric derived from these environments that gives us some kind of uncertainty measures that whether it's sure about this particular action or not. If it's not sure about particular actions, then you may want to explore that further. If it's not sure about particular environment, you may want to explore that further. It's basically this, we made it sure that these environments that we are training gives us some feedback, and then now this agent, right, which was doing completely random, will not be so random because we encourage it to go to the places where it is uncertain about. Right? In the beginning, it may choose to stay and not play the game, and at times that's how you survive the longest. But then it has to move because you want to make it more explorative. It explores into places it is not sure about. That's the kind of metric badges that we're getting back from the environment to make sure that this actually plays the game, or simulates to play the game. And so we record that data in a much more iterative way. To get at this stage, this agent has in a way started to playing game. It's not complete random videos, right? And we now train on these videos generated by the agent that kind of can play the game. So here this is the random agent that kind of doesn't go anywhere. It just keeps on jumping here, right? Now this starts going in the front. You can see that the one at the below is it's automatically start playing the game as much as it can. So that was the CBPR work. Since CBPR, we continued making improvements, and in different fronts. One is about just training bigger models, slightly bigger. It's about higher resolutions mostly and more actions. This video shows you that it's actually better resolutions because you can even see this, read these characters, which you could not read those characters before, because now we have a higher resolution videos that we are training these models on higher resolution. And here you can see that more results on high resolutions, and here we have added actions like you can now shoot, you can go up, you can have different kind of jumps, and you can also have different kind of crouch. So you can do more actions than before. That was the first part of the work. Not sure, I have one more block. How much time do I have? Okay, I'll take 10 more minutes. I'll take that. All right. So then second part is about this world model with the memory. I guess from the title it is obvious, but maybe from this video I will make it, if I can play this video. No. Maybe I can, from there I can do it. Yeah. This is the same kind of videos. You are just going it around, right? And if you pay attention here at the kitchen, I mean you can pay anywhere attention, the kitchen keeps on changing, right? So I guess I just, to make it easier for you to see, I took some screenshots. I hope you can now see that the kitchen is not the same anymore, because this is the 3 times that first time it went away, came back, this is the second time, and the third time it came back again. Okay, it's kind of the similar style, but it's not the same kitchen, right? So it means it doesn't really remember what happened before, doesn't do a good job. So we wanted to kind of extend, kind of improve, maybe it doesn't perfectly align. So general motivation was that previous work that we did at CBPR, what I showed you before, does not use diffusion, and everybody knows that diffusion can give you much more nicer looking videos. Therefore we decided to have a diffusion as a decoder. So most of the diffusion based, even you can call it a world models, they don't really have any kind of memory modeling. At that time there was this idea of the state space model, especially in relation to Mamba, came out, and we thought, okay, let's just put diffusion and Mamba together and see what happens. We do simple things, right? So and then so that hopefully Mamba can help us to memorize, diffusion can help us to generate better videos, right? So that's basically what we did. That here you can see that this is the history frames. You basically get you somehow extract information from history, and this is the history actions. This is the short context that you expose to the diffusion model, and that also has actions eventually embedded somehow, and it predicts the next frame. The thing that it makes different here is that you have this history goes into some state space model, which is actually the Mamba. That gets into this fusion module. Fusion module is basically nothing more than some layered normalization and MLPs and concat. So standard, whatever would come to your mind the first time, that's exactly what's been implemented here. And basically diffusion would give us more pleasing results. State space models hopefully would give us some memory, better memory. For those who don't know about Mamba, I will give you a very brief operating way, because I think it's quite a valuable things to learn. Is that maybe this also would make more sense in relation to the standard transformer block, that you must have seen this transformer block where you can say that this multi-head attention is doing some communication and feed-forward model is doing the computation, right? In parallel to do that, you have Mamba, which is basically the similar block as that of the transformer, that has also a computation block on two sides and one communication block. This communication block now happens different than n square of the multi-head attention. That essentially uses something called selective state space model, and this happens to be very good for language, well, that I will call language, and also from the gene sequencing, not so much for the image understanding or point cloud understanding. People tried it out. I think by now it for obvious reasons, but at that time people tried out how well it goes, because this is indeed be designed with the principle that you have the hidden state, and then you have the inputs, and it's really about the mechanisms of the state transition. You can find more detailed things in the paper. The mechanism of the state transitions, how it needs to be, and to get the next hidden state. That's what this thing does. That's why it's introduced this block quite cleverly actually. And what I like the most is that the way it implements this orange and the green, right? It's actually makes it aware of how GPUs use the compute, because that this has to be very fast, and GPU happens to have, after reading this paper only I found out so that you have got these two parts of these GPUs. One is about this fast part, and then what is about this slightly slower, and then it makes sure that this slower part goes into slower memory, goes this particular part of the state transitions goes into the slower part, and then the update of the hidden state goes into the faster part. And these kind of clever designs, as well as the whole design altogether, makes this SSIM block doing better handling of the memory over time. So in our case, we just use that. Quite straightforward design, I would say. Maybe this is not going to help. Maybe the next slide going to help to you understand better, if I can play the video. Yeah, this is the input. You start and you go around, and you want to come back to the same place. If you come back, you want it to have the same layout. Actually, I had one more video, I think. Okay, I will play it one more time because I got confused myself. Here, this is another video. This is the input. That's the ground truth video. This is the baseline, and this is what you obtain by basically what we are doing is going from one place, different environments, going somewhere else, coming back and seeing whether the layout or stuff's been maintained or not. Of course, in certain scenarios, it's hard. We actually realized that in Counter-Strike kind of games, because often who have played Counter-Strike, you are supposed to go behind the wall and hide. That means you don't really have anything in the field of view, right? And then when you come out and go back, come out and go back, and because of these kind of things, it forgets very, very quickly, because you just lose the visual context. In other settings, when you are going around, right, even if you're going from around and going all the up to here, come back, you may still integrate some kind of meaningful integrations, and it still comes with the plausible results. But if something really goes off in few frames and comes back, then it just creates completely new environments. That's the kind of behavior. It tends to have the diffusion models, but with the right tweaking and adjusting of the Mamba type models, that what we call state space diffuser, that tends to remember better, but of course not perfectly, as you could imagine. So these are just more of the number, that what we do is we train for a length of 50 frames, and it has never seen any longer length than that, and we test for 100 or 150. So somehow it tends to generalize. Here, higher the PSNR, better it is, or the higher the SSIM. That this is the model that's been trained for 50 frames and then tested for 100 frames. And this is the model again trained for 50 frames and tested of 150. Of course, the PSNR goes down quite quickly goes down, but still we were surprised to see that it does maintain like 3 times longer context length beyond what it has been trained. Of course, if you train for longer context length, it does do better job for longer context lengths too. Okay, now I came to the last slide of my talk. Also wanted to keep it brief. That I presented 2 of our recent works. One is about data creations, and then using this data to train an agent and the world model together, so that this agent does explore the environment and then comes up with playable video games without actually having any agent or anyone playing the video games directly. Other one is about fusing these Mamba and the diffusion models to have this state space diffusion models, which now gives us much more realistic and then consistent over the long period of time. So just the takeaway of what I wanted to say is that there are still many challenges and opportunities in this domain. As I said before, that I think this is the very preliminary works and very long way to go, and people in the community are making big bets, including that people who are working in the robotics as well as the 3D scene modeling. There is one company in Silicon Valley called World Labs by Feli. You may know that. They actually are working on the world models too, and so is Jan LeCun and many other people. So this is a quite hot topic, and these are very, very early results in my point of view, and it has many problems to solve. One will be about this long-term memory that I only gave the just a glimpse of it, right? And then handling much more complex dynamics, and then being able to do this physical and behavioral interactions, that if just because there is one person, depending on the character of that person, may behave differently in the scene, right? And exo agents, that so far only you just have ego agents that's moving around the camera doing some actions, that's what we're doing, but then other agents may also do the interactions in the scene. Those are the challenges to address, and the opportunities could be, in my opinion, that we may benefit by the video generative models, that how to exploit them better, because they do indeed generate very, very plausible great 3D what exists out there, and having this dynamic 3D or 4D methods. Or 4D is more dynamic, 3D is what Nicola also presented today, that there also you have some kind of world model, because you can move camera around and have this realistic rendering, right, of stuffs, and maybe you can step on that to build something of the next, not necessarily everything has to be from scratch. And some joint understanding of and the modeling, what I mean to say is that you may actually try to understand and reason with the vision language models, with the world models or the video generative models. There needs to be somehow in the synchrony, and maybe you can judge each other, or you can do both of those tasks, maybe something jointly, so that they can benefit from each other. And learning from virtual environments, not fully explored. And what excites me the most though is about this robot learning, where hopefully we can have such kind of mental model of the world that we can model from the data, video recorded data, right? And then eventually bring that into the robots, that we are also working on this vision language action models robots, and hopefully they can benefit from such kind of visual modeling of the world with the interaction, so that they are aware of how to interact on what they see when they see. This is done with the great students and collaborators as always. Thanks to them, and thanks to you for attending this talk. If you have questions, I'm happy to answer.